Hey there, safety champions. Welcome back to Key Safety Talks.
The YouTube channel where we break down complex safety topics.
Into bite-sized pieces you can actually use
Yeah.
in the world of safety.
We often focus on things like PPE and risk assessments,
Emergency procedures.
all crucial.
Absolutely no doubt. But today,
We're going to zoom in on a fundamental aspect that underpins so much of what we do.
the fascinating world of chemistry.
You're absolutely right. Chemistry might not be the first thing that springs to mind when you think about workplace safety, but trust me.
It's more intertwined than you might realize.
Yeah.
Okay, so let's set the scene. Imagine you're investigating an incident. Maybe there's been a chemical spill, a fire, or even an unexpected reaction.
Having a grasp of basic chemistry can be your secret weapon in figuring out what happened, why it happened, and how to prevent it from happening again.
It's like having a detective's magnifying glass.
For the invisible world of molecules and reactions.
I love that analogy.
It's like having an extra layer of understanding that helps you connect the dots and see the bigger picture.
Exactly. So to guide us through this chemical labyrinth, I've got an amazing expert here with us today.
Oh, well, I appreciate that.
They're a master at making even the most complex scientific concepts clear and relevant to our everyday safety practices.
I'm always excited to share how even a basic understanding of chemistry can empower safety professionals.
To make smarter decisions.
Yeah.
All right, let's get down to the molecular level. Have you ever wondered what makes one substance behave so differently from another? Like, why is water so essential for life, while chlorine, despite being right next to it on the periodic table?
Is a powerful disinfectant.
Yes.
It all boils down to the tiny building blocks of matter, atoms. These little guys are the foundation of everything we see, touch, and interact with.
And thankfully, they're not just randomly floating around.
They're organized in a brilliant system called the periodic table.
Ah, yes, the periodic table. I
Yeah.
remember staring at it in high school chemistry,
Feeling like you were trying to decipher.
an alien language.
Yeah.
But really, it's an incredibly useful tool, right?
Absolutely. It's like a map that tells us the characteristics of each element based on its atomic number,
Okay.
which is simply the number of protons in its nucleus.
So atomic number is like the element's ID number. Got it. But what about those other numbers on the periodic table, like the atomic mass? What's that all about?
That's a great question. Atomic mass represents the weight of the atom, which comes from the protons and neutrons in its nucleus. Now you'll notice that the atomic mass for most elements isn't a whole number, it usually has some decimals. That's because it takes into account the different isotopes of an element.
Isotopes. Now that's ringing a faint bell from my chemistry class days.
Can you refresh our memories?
Yes.
Of course. Isotopes are like slightly different versions of the same element. They have the same number of protons, which defines the element,
Okay.
but they have different numbers of neutrons. So you might have a carbon atom with 6 neutrons, another with 7, and another with 8.
So they're all still carbon because they have 6 protons, but they have slightly different weights because of those extra neutrons.
Exactly.
So it's like having different models of the same car, same basic features, but slightly different engine sizes or maybe extra options.
Exactly. And the atomic mass listed on the periodic table is an average weight that takes into account how common each isotope is in nature.
All right, that makes sense. But here's the thing. Atoms are incredibly tiny, right? How do we actually work with them and measure them in practical situations?
That's where the concept of a mole comes in. Think of it like this. You wouldn't be individual grains of sand to fill a sandbox, right? You'd buy a bag or a truckload, a larger, more manageable quantity.
Okay, so a mole is like a bulk package for atoms.
Exactly. It's a specific number of atoms or molecules that makes it easier to work with these tiny particles. 1 mole is equal to a mind-bogglingly large number, 6.02 by 1023.
Wow, that's more atoms than stars in the universe, probably.
Yeah.
But how does this relate to safety?
Think about those chemical labels with concentrations like parts per million, ppm, or milligrams per liter, mgl.
Okay.
Those measurements are based on moles, and they're crucial for understanding exposure limits.
Ah, so when we see a PL or TLV for a chemical, it's telling us how many moles of that substance are considered safe to be exposed to.
Exactly. Knowing how many moles are in a given quantity of a substance helps us understand how much of a chemical is actually present, which is essential for making informed decisions about worker protection.
Okay, so we've got our atoms, our periodic table, and our moles. But atoms don't just exist in isolation, do they?
Hmm.
They like to get together and form bonds, which is where things get really interesting and potentially hazardous.
You're absolutely right.
Yes.
Chemical bonds are the glue that holds atoms together to form molecules and compounds. And the type of bond that forms has a huge impact on a substance's properties and how we need to handle it safely.
So what kind of bonds were we talking about here?
The two main types of bonds are ionic and covalent. In an ionic bond, one atom basically donates an electron to another atom that needs it to complete its outer shell. This creates oppositely charged ions that are attracted to each other, forming the bond.
It's like a give and take relationship except with electrons.
Yes.
What about covalent bonds?
In a covalent bond, atoms share electrons instead of completely giving them away. Think of it like two people holding hands or both holding onto the same thing, sharing it equally.
Okay, so we've got our atoms forming bonds, creating all these different molecules and compounds. But why is this important for safety? Why should we care about how atoms are holding hands, so to speak?
Because the type of bond directly influences a substance's properties. Think about melting point, for example.
Okay.
A substance with strong ionic bonds will have a much higher melting point than a substance with weaker covalent bonds.
So if I'm dealing with a chemical that has a high melting point, I know I can use it at higher temperatures without worrying about it turning into a liquid.
Precisely. The type of bond also affects flammability.
Okay. How easily a substance will catch fire. Covalent bonds, especially those involving carbon and hydrogen, tend to make substances more flammable. Interesting. So knowing the type of bonds in a chemical can give me a clue about how easily it might ignite.
Exactly. And then there's reactivity,
Okay.
which is how easily a substance will react with other substances. This is especially important when we think about chemical spills or accidental mixing of chemicals.
So a substance with highly reactive bonds might pose a greater risk of dangerous reactions if it comes into contact with the wrong thing.
Exactly. Understanding chemical bonds is like having a cheat sheet that tells you how a substance is likely to behave under different conditions.
That's a fantastic way to put it. It's like having an inside scoop on the chemical's personality.
And that's just the beginning. We also need to think about how these molecules interact with each other in different states of matter, especially gases, which can be particularly challenging when it comes to safety.
All right, let's talk about gases. They're a bit unpredictable, aren't they? They like to spread out and fill any space they can find.
That's right. Unlike solids and liquids, gases don't have a fixed shape or volume.
Okay.
They'll expand to fill whatever container they're in, and their behavior is influenced by pressure, temperature, and volume.
Okay, so we're talking about things like compressed gas cylinders. Those definitely need careful handling, right?
Absolutely.
I remember a case where a cylinder wasn't stored properly and it ruptured when the temperature rose. It was like a rocket taking off.
That's a perfect example of why understanding gas laws is so crucial. Boyle's law tells us that as the pressure on a gas increases, its volume decreases and vice versa. So if a cylinder gets heated up, the pressure inside can skyrocket, potentially leading to a dangerous rupture.
And that's not something you want to experience firsthand.
Definitely not. Then there's Charles's law, which states that at constant pressure, the volume of a gas increases as its temperature increases. And of course, we have the ideal gas law, which combines all these factors into a handy equation.
Can you break down the ideal gas law for us? It sounds pretty complex.
It might seem intimidating, but it's really about understanding the relationship between pressure, volume, temperature, and the number of moles of a gas.
So if we know some of those variables, we can use the ideal gas law to figure out the others.
Exactly. It's a powerful tool for predicting how a gas will behave under different conditions, which is crucial for safe handling and storage.
This is all incredibly insightful, but I can already hear some of our listeners thinking, okay, great, but how does knowing all this chemistry stuff actually translate into protecting workers on the ground?
That's the million-dollar question, and it's where the rubber really meets the road. Understanding these fundamental principles allows us to apply them to real-world scenarios like exposure assessments, hazard identification, and control measures.
Okay, so it's not just about knowing the theory. It's about using that knowledge to make informed decisions that keep workers safe.
Absolutely. We've laid a solid foundation here, and now we're going to build on that by exploring how these chemistry concepts play out in different workplace hazards and situations.
Stay tuned, everyone, because things are about to get even more practical and relevant to your everyday safety challenges.
Yeah. Welcome back to Key Safety Talks. Before we went on, we were laying the groundwork discussing the importance of understanding basic chemistry for safety professionals.
Now it's time to see how these chemistry concepts play out in the field, where the stakes are high.
Excellent. So let's start with something many of us encounter daily: cleaning products.
Cleaning products. I never really thought of them as potential hazards. What's the chemistry behind that?
Well, even seemingly straightforward cleaning products can contain a mixture of chemicals that, if not handled properly, can pose risks.
Okay.
For example, many cleaners contain strong acids or bases.
Oh, right. Acids and bases. I remember those from chemistry class.
We measured them on the pH scale, right?
Yes.
A pH of 7 is neutral, like pure water.
Okay.
Anything below 7 is acidic, and above 7 is basic.
Okay.
The further you move away from 7, the stronger the acid or base.
So things like lemon juice and vinegar are acidic, while baking soda and bleach are basic.
You got it. And the problem is, strong acids and bases can be corrosive.
Uh-huh.
They can burn your skin, irritate your eyes,
Yeah.
and even damage your lungs if inhaled.
Yikes. So we're talking about things like bleach, drain cleaners, oven cleaners, those heavy-duty products.
Precisely. Think about those warning labels you see on these products. They're there for a reason.
Okay, that makes sense. So how do we keep workers safe when they're using these types of cleaning products?
First and foremost, always read the product label carefully and follow the instructions to the letter. Manufacturers provide safety precautions for a reason.
And I imagine personal protective equipment is crucial too, right?
Absolutely. Gloves, eye protection, and sometimes even respirators are necessary to prevent exposure.
Okay.
Think about the specific chemical in the product, its concentration, and how the worker is using it to determine the right level of PPE.
So it's not a one-size-fits-all approach. The PPE needs to match the hazard.
Exactly. And here's where the chemistry knowledge comes in. Understanding the properties of acids and bases, their pH, their reactivity can help you choose the right PPE and implement safe handling procedures.
That's a great point. It's not just about blindly following a safety checklist. It's about understanding the why behind those precautions.
Exactly. Now, here's another common workplace hazard where understanding the chemistry can really protect workers: dusts and particulate matter.
Dust. Seriously, that stuff's everywhere.
Yeah.
What's the big deal about dust from a chemistry perspective?
Well, think about it. Dust is made up of tiny particles of various substances,
Okay.
and those particles can be inhaled deep into your lungs. Now, not all dust is created equal.
Okay.
Some dusts are what we call nuisance dusts. They might make you cough or sneeze, but won't cause serious health problems.
Okay, so like the dust bunnies under my couch, probably not a big deal, chemically speaking.
Probably not. But there are other types of dust, what we call hazardous dusts, that can cause some serious health issues.
Like what? Give us some examples of these bad boys.
One of the biggest culprits is silica dust. It's produced when you cut, grind, or drill materials like concrete, stone, and brick, which contain silica.
Right. I've heard about silica dust being a problem in construction.
It's a major concern. Inhaling silica dust can cause a serious lung disease called silicosis. Imagine your lungs becoming scarred and stiff, making it hard to breathe.
Wow.
That's silicosis, and it's irreversible and can be fatal.
That's frightening. I bet a lot of workers don't even realize they're being exposed to silica dust.
You're right, it's often an invisible hazard. That's why awareness and proper controls are so critical.
So what can we do to protect workers from silica dust and other hazardous dusts?
The good news is there are effective control measures. One of the most important is ventilation, making sure there's adequate airflow to remove dust from the air and prevent it from building up.
So good ventilation systems are a must-have in workplaces where dust is generated.
Yeah.
What else can we do?
Personal protective equipment, especially respirators, plays a huge role. And this is where understanding the chemistry of the dust comes into play.
Okay, I'm intrigued. Tell me more about how chemistry helps us choose the right respirator for a specific dust hazard.
Different types of dust particles have different sizes and shapes.
Okay.
Some are larger and heavier, while others are tiny and can easily bypass a simple dust mask. So you need to select a respirator with the right filter efficiency to trap those specific particles.
It's like choosing the right fishing net. For the type of fish you're trying to catch, the size of the holes in the net needs to match the size of the fish.
Perfect analogy. You also need to consider how much dust is in the air, the duration of exposure, and the health effects of the specific dust.
Right. Those time-weighted averages we talked about earlier come into play here.
Yeah,
We need to make sure the worker's exposure over the workday stays below the safe limit.
exactly. It's all about using the right tools, the right knowledge, and a good dose of common sense to protect workers.
All right, so we've covered cleaning products and dust hazards. Any other workplace scenarios where understanding the chemistry is super important?
Let's talk about flammable liquids.
Okay.
These are substances that can easily ignite and burn, posing a significant fire and explosion risk.
Okay, flammable liquids. That sounds like a recipe for disaster if they're not handled properly.
You're right. Think about workplaces that use solvents, fuels, paints, and adhesives.
Okay.
These substances can release vapors that, when mixed with air, can form flammable or explosive mixtures.
So it's not just the liquid itself that's dangerous, it's the invisible vapors they give off.
Precisely. And here's where understanding the chemistry of these liquids, their flash point, their vapor pressure, their flammability limits becomes crucial.
Flashpoint. Vapor pressure. Can you break those down for us? They sound pretty technical.
The flash point is the lowest temperature at which a liquid gives off enough vapor to ignite if there's an ignition source present.
So it's like the temperature at which the liquid starts to whisper, hey, I could burst into flames if you're not careful.
Exactly. And vapor pressure is a measure of how easily a liquid evaporates.
Okay.
Liquids with high vapor pressure evaporate easily, meaning they release more vapors into the air.
So a high vapor pressure means there's a greater risk of those vapors reaching their flammable limits and potentially causing a fire or explosion.
You got it. Flammability limits are the range of concentrations of a vapor in air that will burn if ignited.
So it's like a recipe. Too little vapor in the air and it won't ignite. Too much and it's too rich to burn. But within that sweet spot, boom.
That's a great way to put it. And understanding these flammability limits helps us to control the environment and prevent those dangerous conditions from developing.
Okay, this is all starting to make sense. But how do we actually apply this knowledge on the ground? What are some practical steps we can take to manage flammable liquids safely?
First, proper storage is essential. Flammable liquids should be stored in approved containers away from ignition sources
Okay.
and in well-ventilated areas.
Then I imagine good housekeeping is critical too, right? Spills need to be cleaned up immediately, right?
Absolutely. Even a small spill can release enough vapor to create a hazardous atmosphere. And again, knowing the flash point and vapor pressure of the liquid helps you understand how quickly and how much vapor will be released.
So it's like a race against time.
Yeah.
The faster we can contain and clean up the spill, the less time those vapors have to build up to dangerous levels.
Exactly. And of course, we need to think about ignition sources.
Mm-hmm.
Things like sparks, open flames, and even static electricity.
I remember a case where a worker was transferring a flammable liquid from one container to another, and they weren't properly grounded. A static spark ignited the vapors, and there was a flash fire. It was a terrifying reminder of how easily things can go wrong.
That's a powerful example of why we need to be so vigilant.
Okay, we've covered a lot of ground here. Cleaning products, dust hazards, and flammable liquids. I'm starting to see a pattern. Understanding the chemistry of the substances we work with gives us a huge advantage in identifying and controlling those hazards.
You're absolutely right. It's like having a secret decoder ring for the invisible world of molecules and reactions.
I love that. It's like we're becoming chemical detectives, using our knowledge to solve safety mysteries and prevent incidents.
And the best part is, it doesn't require a PhD in chemistry. Even a basic understanding of these concepts can empower safety professionals to make a real difference.
I'm feeling inspired to brush up on my chemistry knowledge. But before I dive back into those textbooks, we have one more segment to go. We've talked about everyday hazards, but what about those major chemical incidents that make headlines and send chills down our spines?
Those incidents offer valuable lessons, even if they're hard to hear about. By studying what went wrong, we can learn how to prevent similar tragedies from happening again.
Stay tuned, everyone, because in our final segment, we'll be dissecting some real-world chemical disasters and extracting those crucial safety lessons. Welcome back to Key Safety Talks. We've been exploring how understanding basic chemistry can be a game changer for safety professionals. We've talked about everyday hazards like cleaning products, dust, and flammable liquids. Now let's shift gears and delve into some major chemical incidents that have shaped the way we approach safety today.
These incidents, while tragic, offer invaluable lessons by examining what went wrong
We can identify the contributing factors and develop strategies
to prevent similar events.
from happening again. It's about learning from the past to protect the future.
Absolutely.
Exactly. It's about turning those oh no moments into never again moments. So let's start with an incident that sent shockwaves around the world. The Bhopal disaster in India back in 1984. It's considered one of the worst industrial disasters in history.
The Bhopal disaster is a stark reminder of the devastating consequences that can occur when chemical hazards aren't properly managed. It involved a pesticide plant owned by Union Carbide, where a large amount of methyl isocyanate, MIC gas, was accidentally released into the atmosphere.
MIC gas. That sounds incredibly dangerous.
It is. Exposure to MIC can cause severe respiratory problems, burning eyes, skin irritation, and in high concentrations, it can be fatal. Thousands of people died in the immediate aftermath of the release in Bhopal,
Wow.
and many more have suffered long-term health effects.
That's heartbreaking. What factors led to such a catastrophic release?
Investigations revealed a combination of factors, including equipment failures, inadequate safety systems,
Okay.
insufficient training, and a lack of proper emergency response plans.
So it was a perfect storm of failures that resulted in this tragedy. What lessons can we learn from Bhopal to prevent such incidents from happening again?
Bhopal underscores the critical importance of process safety management. It's about having a comprehensive system in place to identify, assess, and control hazards
Okay.
throughout the entire life cycle of a chemical process.
So it's not just about reacting to incidents, it's about proactively preventing them from occurring in the first place.
Exactly. Process safety management involves everything from thorough hazard analysis and risk assessments to rigorous operating procedures,
Yeah.
robust safety systems, comprehensive training programs, and well-rehearsed emergency response plans.
It sounds like a multi-layered approach to safety where every layer is designed to catch potential problems before they escalate.
That's exactly right. And it's crucial to involve everyone in the process, from frontline workers to managers and executives. Everyone has a role to play in creating a culture of safety.
Speaking of culture, I think the Bhopal disaster also highlighted the importance of transparency and communication with the community.
Hmm.
People have the right to know about the risks associated with industrial facilities in their area.
I completely agree. Open and honest communication is crucial for building trust and ensuring that everyone is prepared in case of an emergency.
All right, let's move on to another incident that provides valuable lessons, though, on a smaller scale than Bhopal. It's the explosion at the West Fertilizer Company in Texas in 2013.
The West Fertilizer Company explosion is a tragic reminder of the hazards associated with storing and handling ammonium nitrate fertilizer, which is highly explosive.
I remember that incident. It was a massive explosion that leveled buildings and caused widespread damage.
Yes, it was a devastating event that killed 15 people and injured hundreds more. Investigations revealed that the ammonium nitrate was stored improperly without adequate fire protection systems. There was also a lack of awareness about the explosive potential of the material among both workers and first responders.
So it seems like a lack of knowledge played a significant role in this disaster.
It did, and this highlights the importance of hazard communication.
Okay.
Ensuring that everyone who works with or might be exposed to a hazardous substance is aware of its properties, the risks associated with it, and the proper safety precautions.
So we're talking about things like safety data sheets, SDSs, right? Making sure they're readily available and that workers are trained on how to understand them.
Exactly. SDSs provide detailed information about a chemical's hazards, including its flammability, reactivity, health effects, first aid measures, and spill response procedures. It's a crucial tool for protecting workers.
And it's not just about having the SDS, it's about making sure workers know how to use it. Training is key.
Absolutely. Training should cover everything from basic chemical properties to hazard recognition, safe handling procedures, emergency response, and the use of personal protective equipment.
It sounds like knowledge is really the best defense when it comes to preventing chemical incidents.
It is. The more we understand about the chemicals we work with, the better equipped we are to handle them safely and respond effectively in case of an emergency.
These incidents are so tragic, but they serve as powerful reminders of the importance of what we do as safety professionals.
They do. Every day, we have the opportunity to make a difference in people's lives by applying our knowledge.
Yeah.
By advocating for safety and by fostering a culture of prevention, we can create safer workplaces and prevent these kinds of tragedies from happening again.
I think that's a perfect note to end on. Thanks for joining us on Key Safety Talks for this look into the chemistry of safety. We've covered a lot of ground today, from the basic building blocks of matter to the devastating consequences of chemical incidents.
It's been a pleasure. I hope our listeners have gained a deeper appreciation for the importance of understanding chemistry in their work and feel empowered to apply this knowledge to make their workplaces safer.
Remember, safety isn't just a set of rules or procedures. It's a mindset, a commitment to protecting ourselves and those around us. And one of the most powerful tools we have in our safety arsenal is knowledge. So keep learning, keep asking questions, and keep advocating for a safer world. Until next time, stay safe.